Now let's talk about aldehydes and ketones, and in this little topic we'll just talk about their nomenclature and properties. Okay, in the next sections you will find the synthesis and reactions. So first of all, a little bit about the carbonyl compounds. This is the first time that you're actually encountering C double bond O as by itself. You've seen it before, you've recognized the functional groups, but this time you'll be dealing with it specifically as to how to make it and then what are some of the reactions. C double bond O is shorter and stronger and more polar than C double bond C, obviously, because you have carbon-oxygen bond instead of carbon-carbon bond. And because of oxygen's electronegativity, it is more polar, all right, which makes the fact that this carbon is going to be more reactive, okay, because oxygen is electronegative, it pulls electrons towards itself, makes carbon a little bit more electropositive then, okay. So here are some of the carbonyl compounds that we'll be dealing with in the next few chapters. So ketones, for example, right here, okay, in ketones again are considered to be internal groups because they are in between two carbons. Then we have aldehydes, which is R, C double bond OH, very similar to ketones, so which means that aldehydes and ketones will have very similar reactions except for a little bit, because here you have two R groups, here you have only one R group. Okay, so we'll talk about how that affects the reactivity of the aldehydes and ketones. Then we have the carboxylic acids, in which case you still have the carbonyl group, but you have an OH, and then acid chlorides, which are C double bond O and then Cl over here, esters with the OR, and amides with the NH2. Okay, but everything that has in common over here is the C double bond O. Okay, that's the carbonyl functional group, and that is common in everything. The carbonyl functional group is different than what we call an aldehyde or a ketone or carboxylic acid, because an aldehyde or a ketone is determined by also what else is there. Okay, as soon as you say you have a carbonyl compound, that just means you have a C double bond O. Okay, it doesn't specify any particular functional group. So let's look at the nomenclature of aldehydes. For all aldehydes, they will end in Al, okay, which is Al. You have to be a little bit careful how you pronounce it, because alcohols end in OL, whereas aldehydes end in Al. So for example, the smallest aldehydes would be methanol, ethanol, propanol. And so you have to be careful that you're not saying ethanol versus ethanol, okay? And so be careful about that. Aldehyde carbon is always going to be the number one carbon, because aldehydes are terminal groups, which means they're always going to be hanging out there somewhere, so you kind of know always, okay, that there's an aldehyde. If you have a CHO that is attached to a ring, then you use it as a suffix, okay, as a carbaldehyde. So this one here, for example, would be a carbaldehyde. If in a molecule you have a ketone as well as a CHO group, then and something else has higher priority than that, and something else that has higher priority is actually carboxylic acid, then the CHO group will be called formal, okay, and the C double bond O as a keto group would be called oxo, okay, and we'll see some examples of that also. Between the aldehyde and a ketone, aldehyde gets priority because it's a terminal group. So here are some examples. Let's look at the first one. Here we have an aldehyde, and here you have the chain. So let's start counting from the terminal carbon, which is this one. Okay, so 1, 2, 3, 4, 5. So which means we have pentanal, and on the third carbon there is a methyl group. Okay, very simple nomenclature. Here the carbaldehyde group will be used as a suffix, okay, as we said here, and then everything else you name as whatever it is. Okay, so this is cyclopentene. And then on the second carbon from the carbaldehyde, okay, from the aldehyde is where the alkene starts. Remember, aldehydes will get priority, and that's why you're not including the double bond here. And then in the numbering actually starts from the substituent, okay, as usual. So 1, 2, cyclopentene, carbaldehyde. Then we have this compound. Now in this case, if there was no CHO, you'd be calling this benzoic acid. If there was no carboxylic acid, you'd be calling this benzaldehyde. Okay, but because you have both of these, carboxylic acids take precedence over aldehydes, so which means you have to call this formal group. So this is 3-formyl benzoic acid. Okay, here is another example, and in this case we have a ketone as well as an aldehyde. Okay, so and we also have a methyl group over here. So 1, 2, 3, 4, 5. So we have a pentanal. This takes precedence, so you end it with pentanal. On the third carbon, you have a methyl, and the fourth carbon, you have an oxo, which is, of course, the ketone group. The way you would number all of this and name all of these substituents would just be alphabetical, as you have learned before. Aldehydes have been known for a long time, so they have common names also. Their common names are based on acids, because acids have also been known for a long time. So for example, if you have a one carbon acid, carboxylic acid, it's called formic acid. And I know we'll do this more when we get to carboxylic acids, but this may be just a preview, okay, of what's to come. So anyhow, one carbon carboxylic acid is called formic acid. And so the aldehyde with one carbon is known as formaldehyde. So you drop the ic acid and add aldehyde, all right, to it. So formaldehyde is your first aldehyde. And as I'm saying the name, it might ring a bell also, because we know formaldehyde. Acetic acid is two carbons, and you've seen acetic acid before. You've done this in equilibrium a lot. And then the two carbon aldehyde would be called the acetaldehyde. So two carbon, then IUPAC name would be ethanol, but this common name is acetaldehyde. Propionic acid is for three carbons. Propionaldehyde is for three carbon aldehyde. Butyric acid is for four carbon acid. Butyraldehyde is for four carbon aldehyde. Okay, and so here's the general name for a butyraldehyde name compound. Most of the time you will actually get IUPAC nomenclature for aldehydes and ketones, but these first two, formaldehyde and acetaldehyde, are very common, so you should learn them. Okay, propionaldehyde maybe not so much also because you don't encounter it so much, but 1, 2, 3 at least you should know. Okay. Let's talk about the nomenclature of ketones now. The nice thing about ketones is they all end in -one, not one, -one. And so it's easy, okay, to figure out whether you have a ketone or not. And again, you start the numbering from the carbon which is closest to the ketone. That's where you start. For cyclic ketones, you start the numbering where you have the ketone. Okay, so let's do some examples here. Here we have a ketone with 4 carbons, and the carbon closest to the ketone is on the left. So 1, 2, 3, 4. So it's a butanone. And on the third carbon, you have a methyl, and the ketone is on the second carbon. So because ketones are central groups, you have to number them also. With aldehydes, we didn't have to do it, because with aldehydes, that was the numbering carbon, and those are the terminal carbons. You have to start numbering from there. But with ketones, you can't start to number from the ketone, especially in straight chains. However, in cyclic compounds, you don't have to give it a location, because you are starting your numbering from the ketone. So here is the ketone. This is cyclohexanone, cyclocompound, 6 carbons, and ketone. So cyclohexanone, and then on the third carbon from the ketone is bromine. So it's 3-bromo-cyclohexanone. Again, this is kind of similar to the first one, except now you also have an alcohol. So the way we would have an alcohol there is an hydroxy. Okay, and hydroxy is the substituent name for alcohol. So this is still 3-methyl, 2-butanone, but we also have 4-hydroxy now. Okay, so 1, 2, 3, 4, and the fourth one, there's a hydroxy group. Again, go ahead and number all these things and write all these things alphabetically. Okay, except for the 2-butanone here, because these go together. So here are some more examples, and this is interesting because in some cases we can also name whatever is on the either side of ketone. Okay, so let me show you for this one. Okay, on the top here. So methyl isopropyl ketone. So this is a methyl group and this is an isopropyl group. So keeping the keto carbon in the middle, you name whatever is on either side. So in a methyl isopropyl ketone, you really cannot tell how many carbons you're talking in the long chain. So you start your structure by drawing out the ketone. You write out the ketone, and on either side you write the methyl and the isopropyl. So if you have to convert a general name to an IUPAC, you have to write it out, okay? The names in the red over here, by the way, these are the new IUPAC systems where you have to give the location of the functional group just before the functional group. Okay, so butane 2-one. That is how this would be called. 2-butanone was the old nomenclature. Butane 2-one is the new one. That's what you will find here also. Okay, here is acetone. Acetone is really weird in its nomenclature because acet for us would mean 2 carbons, but this really has 3 carbons. So if you cover up this CH3, this is 2 carbons. I know it's kind of weird, all right, but that's how it is. And so this is the acetyl group, kind of, if you remember from when we were talking about Friedel-Crafts reactions. This is the acetyl group, okay, COCH3. And so this acetyl group, then if you add a CH3 here instead of a Cl, if it would be a Cl here, we would call it acetyl chloride. But because we have a CH3 here, we call it acetone. Okay, and so it's really weird, all right? You can also call it dimethyl ketone because here are 2 methyl groups on either side of ketone. You can also call it, yes, 2-propanone. Okay, 2-propanone because this is on the 2nd carbon and you have 3 carbons here. Acetophenone you have dealt with before. We talked about this in benzene nomenclature. This is also called methyl phenyl ketone. Okay, so if you kind of are making the connection, the nomenclature of ketones is kind of similar also to ethers. Okay, when in ethers also we name the left and the right hand side of the ether. Here also we name the left and the right hand side of the ketone. All right, here is benzophenone or diphenyl ketone. The physical properties of aldehydes and ketones. So first of all, for boiling points, okay, aldehydes and ketones are more polar than alkanes, all right, so they will have higher boiling points. What that also means is that even some of the smallest aldehydes and ketones you find are going to be liquids, okay, so for example, acetone you deal with all the time in the lab. It's kept in a wash bottle. It's a liquid. It evaporates really fast. So it has a lower boiling point. It has a low boiling point, but it's not that low, okay, which means that it exists as a liquid, all right. Even the simplest aldehyde, acetaldehyde, occurs as a liquid, all right. And so all the aldehydes and ketones are going to be liquids, and then of course as you get to the higher molecular weight, they get into being solids, all right. So here are some comparisons across the functional groups that you have learned so far, all right. Alcohols will have the highest boiling point because of hydrogen bonding. Aldehydes and ketones, not so much because there's no hydrogen bonding here, but there is polarity, all right? And then alkanes have no polarity whatsoever, no polarity, no hydrogen bonding, nothing going on for it, okay? So that's how the physical properties vary across the functional groups. Solubility is similar to what we call in the boiling points also because of the polarity. They are still a little bit soluble in water, but after a while, as you get to higher molecular weight, then the solubility decreases, okay, in water. But they are definitely good solvents for alcohols, okay, because they're similar in nature. They're both polar, so they do dissolve all organic compounds and of course in alcohols, okay. The small aldehydes and ketones are soluble in water. One of the things about the aldehydes and ketones is their odor. Okay, they are very characteristic odor, and a lot of these aldehydes and ketones, as we'll see in future slides, they're very good flavoring agents. They also make for very good perfumes. Okay, because they just smell very nice. Okay, and so aldehydes have some of the most unique aromas. For example, vanilla and benzaldehyde. Benzaldehyde is found in almonds. Okay, so if you like the flavor of almonds, that's benzaldehyde. And who does not like vanilla? We all love vanilla. Ketones are usually the sweeter smelling of both of the functional groups. So applications of aldehydes and ketones. Formaldehyde is a very common preservative agent, okay, and that's where you might have heard of it. It's called formaldehyde or formalin. Formalin is a polymer of formaldehyde, okay, in a way. It's a little bit of a polymer, and that is, it keeps tissue for a long time. And then Bakelite is also a polymer of formaldehyde, and Bakelite is one of the strongest polymers out there. Okay, and so it's a very good polymer um, of aldehyde. Some of the odors of aldehyde, okay, as we said, vanilla. This is vanilla over here. Here is the aldehyde group. Then there is cinnamaldehyde. I forgot cinnamaldehyde. How could I have forgotten this? Cinnamaldehyde, wonderful smell. That also is an aldehyde. Benzaldehyde is the almonds. Nonanal is roses. Yes, okay, roses. If there was no nonanal, there was no aldehyde, a rose is just a paper rose then, okay. Octanal is the citrus smell that you get, and so on. So you see over here that all aldehydes, they smell, okay, and most of these are really quite pleasant smelling things. There's one thing that you should be aware of, that a lot of these compounds, they do smell. So for example, benzaldehyde does smell like almonds, but if you open up a bottle of benzaldehyde and stick your nose in it, which you should not be doing anyway, but if you take a whiff of it, it's not going to smell like almonds, because in almonds there's a very, very small amount of benzaldehyde. So you get the flavor of it. You're not dousing yourself in almonds, okay? And so all of these smells, these compounds will not smell like that. You will, if you take a general whiff of it, very small amount, then you will get the smell of it. Otherwise, you may not get it. You'll just overwhelm yourself with some of these smells. Ketones, acetone, very, very common solvent. Okay, we cannot live without acetone. Organic chemists swear by acetone because this is what keeps our glassware dry. So very, very common solvent. And then there are a lot of terpenes out there. Okay, terpenes are a very specific class of compounds with a very specific structure. We talked about that back when we were talking about conjugated systems. And so terpenes are a very specific class of compounds. And they have this kind of a fragment. They're based on 5 carbon units called isoprene. But anyhow, all of these have very sweet smells. Okay, so for example, camphor, very sweet smelling. Carbone, very sweet smelling compounds. And eugenol, okay, that also is a ketone. And so you'll find ketones that are used also as what you call perfumes. Okay, so very, very common. And then you find ketones also in steroids. Okay, so here are some examples for steroids like hydrocortisone, progesterone, testosterone. They all have the keto functional group in them. Okay, and so a very common functional group that you find in so many compounds. So for this little topic here, you should definitely know all the nomenclature, the physical properties. Yes, you will have to compare all across the board from all the functional groups. The applications was just for your GK, general knowledge.